Okay, into our final video on this topic and this subtopic. And in this video, we are going to look at nuclear fusion. I promise this won't be as long as the last video. Okay, nuclear fusion, really important process. This is the process that's occurring in our sun that keeps providing the energy to keep us all alive. If you haven't already, have a look at this nuclear fusion video from Fuse School. Gives a really good introduction to it. So firstly, nuclear fusion is the process in which two nuclei combine into a single nucleus. And generally, where nuclear fission was a large nucleus splitting into two smaller nucleus, nuclear fusion is two small nuclei combining to form a larger nuclei. Probably the most common example a couple of common ones, is helium-2, which we call deuterium, helium with 1 proton, 1 neutron, and tritium, helium with 1 proton and 3 neutrons, can combine to form helium-4 and to also release a neutron. Both of these get released with large amounts of energy, millions of electron volts. I briefly talked about that in the previous video. The process that's occurring in the sun is where hydrogen is basically fusing together to initially combine different hydrogen to form deuterium, another isotope of hydrogen. You've got some other processes happening there, like like beta minus, beta plus type decay processes. And eventually the final product of this reaction is helium-4, just like our old alpha particle from before. But again, in this case, the mass of the nuclei that we start with, whether it's the deuterium and the tritium or the just simple hydrogen, is greater than the mass of the final helium nuclei that we finish up with, and we basically have the mass that is lost being converted to energy, which we can work out using the same formula, E equals mc squared. The big challenge with nuclear fusion is, well, let's talk about this. For fusion to occur, high kinetic energies are needed to overcome the repulsive electrostatic force between nuclei. So when we try and push two hydrogens together, they're both positively charged. Like charges repel, we have got to get a huge amount of energy to push these close enough together to overcome electrostatic repulsion and to get into that region where they're so close that the strong nuclear force takes over and holds them together. So to allow the nuclei to approach within a very short range of the nuclear attractive forces, so the strong nuclear force we're referring to there. There is a huge amount of work going on to try and replicate this process on Earth, because producing energy this way will produce massive amounts of energy in the same way that nuclear power does, but it doesn't produce the radioactive waste. We actually have a helium shortage in the world now. We'd help solve the helium shortage. And helium, don't breathe it in. It makes your voice go squeaky, but it's not a particularly toxic gas as such. So, not compared to radioactive gas. However, why can this happen in the sun continually, but we can't recreate that in a sustained way on Earth? Well, that's because we need so much energy to push them closely together. How does the sun do this? So two factors maintain nuclear fusion reaction within the sun. The large mass means the gravitational force is massive, holding the atoms in very close proximity. So the sun is massive. Gravity is so strong, it really holds those atoms closely together, much more closely than they would be held on the Earth due to gravity. So that's the starting point. The products of nuclear fusion have also huge amounts of kinetic energy, and when they collide with the hydrogen atoms, they transfer that energy to them. So when these helium that get produced, they will collide with other hydrogens, they will give them large amounts of energy, and that energy helps force them close enough together to overcome electrostatic repulsion and to fuse together, releasing large amounts of energy. As I sort of hinted at before, the total mass of reactants in a fusion reaction is greater than that of the products, releasing energy given by E equals m squared, where delta m is the mass of the reactants minus the mass of the products. So we can do calculations like I did at the end of the previous video to work out how much energy is released. I'm not going to go through those. Again, it's exactly the same process as before. And I think, yeah, have a look back there if you need some assistance with that. That's it for nuclear fusion, and that is it for the nuclear models and radioactive topic. Thanks for watching. Remember, if you like this video, click like. If you want to see more of this sort of stuff, click subscribe. Cheers.